Today, I'd like to present our work ROIAL, a region of interest active learning framework for characterizing exoskeleton gait preference landscapes. Our research is centered around developing dynamically stable crutchless gaits for lower body exoskeleton walking, aiming to restoring mobility for patients with paraplegia. Specifically, we work with this exoskeleton you see here in the video, Erdem, which is designed by a French company, Wondercraft. The exoskeleton's walking gait is parameterized through a set of variables such as step length and step duration. You can see how these parameters influence the walking behavior here. The gait on the left moves really slowly compared to the one on the right. Different users usually have different gait preferences. It remains unclear how we could select the specific values of these gait parameters for individual users to maximize user comfort. Prior work on learning exoskeleton users' preferences tried to tackle this problem directly by optimizing with respect to user comfort, aiming to identify optimal gaits for specific users. However, because it prioritized converging to the best action, the posterior model only gave us reliable information around this optimal gait. In this work, instead, we would want to focus on an alternative goal, understanding. This approach prioritized reliably learning the entire landscapes. We believe that characterizing the entire landscape will allow us to study common patterns across users and yield insight into the underlying science of walking, which are things we cannot do with just information around optimal gaits. However, during the process of active learning, it's likely that user will be exposed to actions in the region with low utilities, like the one circled here, which will lead to subject discomfort. Hence, our goal is to characterize the relationship between exoskeleton walking parameters and user preferences without exposing users to too many gaits that make them feel uncomfortable. We frame this problem as active learning within a region of interest. We assume that for each gait A, there is a utility FA associated with it. During the experiment, we collect subjective feedback from users because usually they're more reliable than numerical score. The feedback we're collecting include peer-wise preferences, which is essentially feedback in the form of, I prefer the current gait over the last gait, and ordinal feedback, which are order labels such as good or neutral that users could give for the gaits they experience. We collect preference feedback because it's been shown to better recover final grain differences in utility. However, since it only provides relative information and does not indicate user comfort globally, we supplement preferences with ordinal feedback to help us identify the region of interest quickly. We define the full feedback dataset D as the union of the previous two datasets. In the exoskeleton experiment setting, we consider four ordinal categories: very bad, bad, neutral, and good, each denoted by a set OI, where I is the rank of the category. We define our region of avoidance to be the least preferred ordinal category O1, and our region of interest to be the remaining action space. The green curve here represents our true utility function F. The action space is split based on the region of avoidance threshold, denoted by B. If the utility of the action is smaller than the threshold, then it belongs to the region of avoidance, which is indicated by the orange shading. Alternatively, if an action has a utility that is greater than the black threshold line, then it belongs to the region of interest. Our learning objective is to maximize the accuracy of the utility model in the region of interest. We denote our model's MAC estimate of F by F hat, shown in blue here. We would like the blue F hat line to approximate the true utilities in green as accurately as possible in the region of interest, but do not care how accurate F hat is within the region of avoidance. We can evaluate performance by measuring how accurate the map utility estimate F hat predicts preference and ordinal labels in the region of interest. The general process of how ROIAL works is illustrated as following. At each iteration, we first collect the user feedback on the sampled action. We use Gaussian process to jointly model preference and ordinal data. Then we estimate our region of interest using the posterior and select action that maximize the information gain inside the estimated region of interest. First, I'm going to talk about how we use Gaussian processes to model the utility function for the user's preference and ordinal feedback. Given the feedback dataset D, Utilities F have a posterior proportional to the product of the preference likelihood, ordinal likelihood, and prior. Here's an example of a Gaussian process posterior, where the blue shaded region indicates the model's uncertainty via 2 standard deviations about the mean. The green dotted lines are samples of utility functions drawn from this posterior distribution. The Gaussian process prior, defined by the equation here, encodes that the utility is smooth in the input parameter space. In this work, we use squared exponential kernel for the covariance matrix. We assume that preference feedback can be corrupted by noise. The greater the difference between the utilities of the two compared actions, the more likely that the user gives a correct label. And the function g here is a monotonically increasing link function. For ordinal feedback, each ordinal category is bounded by ordinal thresholds by and by minus 1. The greater the total difference between the utility of this action and each of the two corresponding ordinal thresholds, the more likely that the user will provide the correct ordinal label. As shown in the likelihood plot for the case with 5 ordinal categories here, the likelihood peaks at the center of each category. After we obtain our posterior, we need to use that to estimate our region of interest to avoid sampling from region of avoidance. The green function f is the true utility function that we want to learn. We assume that there is some threshold on the utilities such that the action in the region of avoidance has utilities that fall below this threshold. Now f hat is our model's best estimate of where the utility function f lives, and it has some associated uncertainty with it, indicated by the blue shading. We call the true region of avoidance threshold b, while the region of avoidance threshold in the model b hat. In each iteration, we estimate the region of interest as the set of actions that satisfy the following criteria: f hat a plus some constant times the action's posterior standard deviation exceed the upper dotted line b hat, which are essentially the region outside of the orange shading. As the learning duration increases, we hope that our f hat and b hat are getting closer and closer to the actual values of f and b. After we obtain our estimated region of interest, we'll select an action that maximizes information gain inside this region. Previous work has shown that a greedy approach, which only optimizes with respect to the next immediate action, achieves state-of-the-art data efficiency. Here, we adopt the same strategy. Specifically, we aim to find the action within the region of interest that maximizes the mutual information between the utility function and the preference and ordinal feedback. This would lead to the greatest uncertainty reduction in the utility given the feedback outcome. This term can be rewritten in terms of information entropy. The first term can be interpreted as the uncertainty about the action's ordinal label and preference relative to the previous action. We want to maximize this term, since queries with high model uncertainty can yield significant information. The second term is conditioned on f, and so represents the user's expected uncertainty. We want to minimize this term, because if the user is very uncertain about their feedback, then the query would only give us a small amount of information. We approximate the information gain via sampling from the Laplace approximated Gaussian posterior. We'll now illustrate this learning process with a one-dimensional example. Initially, ROIAL samples widely across the action space. After iteration 5, ROIAL stops querying points in the region of avoidance because in that area, the posterior upper confidence bound falls below the region of avoidance threshold. We can see that after 20 iterations, ROIAL learns a much more accurate model in the region of interest. Here, simulation results with 3-dimensional functions. ROIAL successfully captures the region of interest and learns the utility landscape more accurately as the number of learning iterations increases. We deploy the algorithm on the lower body exoskeleton Erdem to learn 3 non-disabled users' preference landscapes over 4 gait parameters: step length, step duration, pelvis roll, and pelvis pitch. In the learning process, users were asked to give each trial 1 of 4 ordinal labels: very bad, bad, neutral, or good, and were then asked whether they prefer the previous or current trial. There were in total 30 training trials and 10 evaluation trials per subject. We plot the confusion matrix for all 3 subjects' validation trials. The first column is gray because actions in the region of avoidance were purposely avoided to prevent subject discomfort. The actions that are predicted to be in the ordinal category O2 indeed mostly belong to O2 according to users' feedback. In general, we saw a reliable correlation between predicted categories and the user's provided ordinal feedback. We evaluate the effect of each gait parameter on the posterior utility. To visualize the 4D posterior, utilities are plotted over each pair of gait space parameters, with the values averaged over the remaining 2 parameters in each plot. Each row here corresponds to one of the 3 subjects. These learned landscapes highlight both regions of agreement and disagreement among the subjects. Specifically, if we take a look at the first column, which are posterior over step length and step duration, we can see that all subjects disagreed in the most preferred regions, which are circled in the plots across these 2 dimensions. Now let's take a look at the last column, which are posterior over pelvis pitch and pelvis roll. The circle regions here are the regions with the lowest utilities. We can see that all subjects strongly dislike gaits at the lower bound of pelvis pitch and pelvis roll. In summary, ROIAL actively learns utilities over a region of interest that ensures user comfort by learning from online human feedback in the form of preferences and ordinal labels. Experimental results demonstrate the feasibility of recovering gait utility landscapes from limited human trials. Future work includes studying the gait preferences of people with paraplegia, quantifying the noise in the feedback, which may depend on users' prior experience and be biased by the order in which they experience the gaits, and most importantly, using these learned landscapes to generate new exoskeleton gaits tailored toward users' preferences. Thank you for listening. Feel free to send any questions to us via email.